Let's get started with part one of Lab 7. In this part, we'll try to understand various properties of NetFPGA, the network properties, I mean, and then how it performs in high traffic conditions and stuff like that. For this, we'll develop a topology with the PC containing the NetFPGA connecting to four other nodes or PCs through the four ports of NetFPGA, right? And then we can deploy that on data test bed, and then we can see how it works. So first step is to actually write an NS file, the NS script. So as per our required network topology, IP address configurations, then we created an experiment using that NS script, and the experiment has been swapped in, right? So let's see if we actually were successful in creating the network topology desired. So when we go to the visualization section, that shows what we ended up creating. So let's bring up more details on that. Yeah. So as you can see here, we were successful in creating the topology desired. So we have a control node, that is the PC containing the NetFPGA in the center, and then you have N0, N1, N2, N3 nodes connected to that through NetFPGA ports, right? So the IP addresses of the nodes have been configured in the NS script, but we didn't configure the IP addresses of the NetFPGA ports. So that we have to infer looking at the details provided by the data test lab itself, right? So let's scroll down a little bit after this. Yeah. So you can see here these parts indicate actually the IP addresses, and this part indicates the MAC addresses of various interface, right? So from this we can infer the IP addresses of individual ports of NetFPGA. So the same details have been mailed to us by Data Lab, so you can also find that in inbox. So how we can reduce the IP addresses of each port of NetFPGA is that the MAC address, the last octet of the MAC address, actually contains the port number of NetFPGA, right? So you can see this, the last octet of the MAC address is 03, right? That means that's NetFPGA port number 3, and its IP address is 10.1.0.2. So similarly, you can see reduce the IP address of port 0, and this is port 2, and this is port 1, right? So now what we can do is we can go to the control node and configure these interfaces, right? So the control node runs a CentOS. So we'll first SSH to the users.isi data lab. So that's how their server works. So first have to go into that, and then let's tunnel into the control node, that is the PC containing the NetFPGA. So you can see that we were successful. Now we'll first do a CPCI reprogramming. That's like wiping the slate clean, and so yeah, okay. So now we can start configuring the interfaces manually. So see, NF2C3 here indicates that the NetFPGA port 3, and looking at the details, we can write the IP address here, and then similarly we can do for we can do the interface configuration for other ports, right? So this is for port 0, and now we'll do for port 2, yeah, and then similarly for port 1, right? So we were successful in configuring the interfaces with correct IP addresses, right? This might seem like we are good to go. Let's actually check if the ping is working. I mean, like if you're able to ping other nodes, right? So first we pinged N0, and as you can see it says destination host unreachable. That means we could not talk to N0, right? So let's try to ping N1 and see what happens. So same response, right? So we are unable to talk to any of the nodes that's outside of our own PC. So why this is happening is because the the NetFPGA is blank, right? So it's kind of blank. So we don't have any design loaded onto NetFPGA. So we would have to first load a design, and then make it talk to other devices. So first we'll actually load a reference NIC design. So the reference NIC design is already provided to us by the NetFPGA developers. We can load that using nf_download command, right? So let's do that. So as you can see, we now the reference NIC bit file is loaded onto the NetFPGA, right? So let's try to ping now. So basically, this is the reference network interface controller card, right? So let's try to see if ping is working now. First, we'll ping and not. So as you can see, the ping is working this time, right? So we are able to talk to N0 and no packets were dropped, right? So let's talk to N1 now. Let's see if that works. Yeah. So as you can see, the ping is working now. So this shows that the reference NIC design does work, and we have configured everything correctly. So that we can talk to other nodes. Let's try to vary some parameters and see how it affects our throughput, right? So the very first thing we'll be doing is going into N0 and N1 nodes and then changing their read and write buffer sizes, right? So since we have a gigabit Ethernet connection here, to actually test the bandwidth and throughput, we have to make sure that the buffer is big enough, right? So let's try to change that. So let's first go into N0 and change its read and maximum read and write memory buffer sizes, right? So these two commands do that. Now yeah, we were successful in configuring that. Let's try to do it for N1, right? So first we tunnel into N1. So now we can run the same commands, thereby increasing the read and write buffer sizes on N1. Means these parameters. Now let's try to run the server on N1, client on N0, and then see, look at what the TCP throughput is, right, for this reference NIC design. So here you can see that we are running a server on N1 and we are making N0 the client, right? So let's see what is the TCP throughput we'll get through this. Okay, so as you can see, the TCP throughput is just 167 Mbps. This is very low, considering that our bandwidth is actually 1 Gbps, right? So that's the maximum bandwidth possible, right? But we are getting nowhere close to that. That is happening because as the packets, let's say the packets are going from N0 to NetFPGA and then to N1. So what's happening is when the packets go from N0, they enter the port of NetFPGA, and then they have to be taken up to the software, right? The CentOS running on that NetFPGA there, right? So that is a software component of NetFPGA, and then those packets have to be processed, and then the routing decisions have to be made, and then they have to be sent back to the hardware, that is the NetFPGA, and to appropriate ports there, and then to N1, right? So that's a very long process, right? So that's why it's taking so much time, and hence the TCP throughput is very less. Now for the next phase of this, let's try to download the reference router kit that's already again provided by the NetFPG developers, and see, run the same tests again and see what throughput we can get, right? So let's do that again. nf_download, this command helps us download the bit file. So this time we are downloading the reference router bit file onto the NetFPGA, and we were successful, right? So the this also requires the reference router also requires a routing kit daemon. So that's a process that's that'll be running on the Linux. That is a CentOS system. So what it does is so basically all the OSPF, BGS, all the IP routing algorithms will be still running on software component. So the routing tables that will be generated in the software, that will be reflected by this daemon onto the hardware. So whenever the packets come, the routing, a part of routing table is already there in the hardware. The hardware can just perform a simple lookup, and then the packets can get routed to their destination. So let's get the RKD running. That is the router kit daemon. So this is the process ID of the RKD, right? So now let's run the same tests again, right? So I'll make this a server and I'll make this a client. So let's see that. Oh, okay. So as we can see, the kind of throughputs we are getting is almost you can say at line rate, right? So 942 mbps, around 940 mbps is the TCP throughput that we are getting. Considering the previous case where we had around 140 mbps, this is a very huge increase. Automate this process of creating servers and clients on various nodes through a shell script, and then we'll try to generate a lot of network traffic and see how the throughput gets varied, right? So first let's have a look at the shell script that I have written, right? So this is the shell script. So it basically starts servers on each of n0, n1, n2, n3 nodes, and also correspondingly starts a client in each of these nodes. For example, if you started a server on n0, it starts with n1, and then for n2 it starts with n3, and it goes on, right? So and then the test runs for 30 seconds, and the length of the packets or datagrams that we are using is 512 bytes, right? So we are purposefully using small packet sizes to see what happens to the performance, right? So let's first actually download a reference nick design to test this shell script out. Yeah, so reference nick has been loaded to the NetFPGA. Now let's run the iperf, that is the shell script that we wrote, right? iperf underscore test.sh. So we started the servers, clients have connected. So the test goes on for around 30 seconds. Let's skip to that part. So as you can see, just ignore the first four lines. That's initially when the network traffic is not high. Now when the network traffic is quite considerably high, you can see that the throughput is just like around 40 mbps, right, for the reference NIC design. So this is very low, right? This is not even considerable, taking the fact that we have a 1 gbps link. Now let's try to run the same test but with a reference router design loaded onto NetFPGA. So the reference router bit file has been loaded. Now let's have the RKD up and running. Yeah, okay. So now we'll again run the same shell script. The servers are up and running, the clients are connected again. So now here you can see the report. Have a look at the report that we are getting a TCP throughput of 800 mbps, right? So that's very high compared to reference NIC, but that is still low compared to the throughput we used to get, right? So that is because the small packets, the small size of packets is actually stressing the system out, right? The NetFPGA system. That is the reason the throughput has decreased overall. Right. So Let's look at the second part of Lab 7. So in the second part, we are asked to design a pass-through IDS. So that's just basically a block that sits there in the data path, and then that just without doing any processing, just connects the input to the output, right? So we did the modification to the IDS block that was given to us. That is the .v file that was given to us. The interface remains the same, right? So it has the input data, input control, input write ready, and then it gives the output ready to the block that is above it, right? So the block above it is output lookup, and after that it has corresponding output ports, right? So that connects to the block next to it, right? So apart from that, we have a set of register interfaces. So we are also asked to design hardware and software registers. So these interfaces are for the requests of those, right? And then apart from that, we have reset and clock. So let's look at the logic first. So it's a very simple logic. It just ties the input to the output, right, through with the wire. So it's a simple set of logic there. And then so if you look at the register part of it, right? So first, we are using two software registers and one hardware register here, right? So one of the software registers is IDS underscore command. So that is used to store the the command that we pass through command line interface. And then IDS underscore software reg is one another thing where whatever we pass argument, that arguments get stored, right? So that is accessible to the hardware. So hardware basically takes the value stored in that IDS underscore software register and does some manipulation, and then stores the result back in another hardware register called IDS underscore hardware register, right? So I'll explain to you like what the functionality is and what processing the hardware does and how do you interact with that, right? So I'll first describe the declarations we have done in IDS underscore XML file, and then come back to the logic, right? So here, the NetFPGA documentation says that first all the blocks, all the modules that are used, right, in the project, they're defined in project.xml. So the modules become visible, right? And then after that, if we have any registers for that module, that has to be declared in that particular module.xml, right? So this is the module that contains that, right? So here you can see that IDS underscore software register, IDS underscore command, and IDS underscore hardware register, right? All of these registers have been made to be a 32-bit register, right? So that has been declared. Now let's look at the functionality. Like, so what do we do with the data, right? So just a second. So what you can see here is at every tick of clock. So what we basically do is we take the 32-bit data that we're getting, that is the 4 bytes data in software register. We are just swapping, reversing the byte order, right? So the LSB byte in software register becomes the MSB byte for hardware register. So similarly, so this just swaps the byte order, right? It's a very simple function that has been implemented, and that is written to IDS underscore hardware register, right? So that has been done. And so how we pass the interface, we just pass, we instantiate this generic registers module, and then we send the input and output that are required for register interfacing, right? So as we had a look at the NetFPGA design, the register, the pipeline is different for register this thing, right? So for all the registers in each block, they have a separate pipeline, right? And then our whole block is included in user data part.v. So you can see that, just a second. See, pass through IDS. So that has been connected. So it's getting its input from the output lookup, the block that is above it, and then it's sending all its output to the output queue module that is below it. Now let's look at the Perl file, the Perl script, right? So to pass arguments through command and how it's interpreted and what are the various functionalities, right? So so we are storing whatever command that we pass through, right? So that we are first storing in the dollar command variable here, right? So basically if we like if we have with the high, if we want to describe the design at a high level, so it basically has you have three commands that you can pass through, right? The first command is reset. This resets all the values in all the registers basically. And then you have a write software register, right? And then you pass a value to it for that. So again, as I told you, whatever value you pass through in through command line interface, so that is an ASCII. So that value will be converted to hexadecimal, and then that will be stored in a register. So that can be accessed by hardware, and then that data can be processed and then written again to IDS underscore hardware register, right? So this is the Perl script that does that, right? So we take the argument. So whatever the argument that we passed in, the first argument, so that has been taken into a variable called CMD command, right? If the command is reset, we do IDS reset, right? We do this subroutine. Yeah. So this basically resets the command, right? Register. And then if it is if the command is write software register, right? So if we so the write software register actually requires two arguments, right? The first is the command itself, write software register, and then the actual value, right, that we want to pass in. So again, if the number of arguments is less than two, so we'll be directed to another uh, subroutine called usage, right? So that basically describes like how do you use this, right? So that's there. And then yeah, if the number of arguments is equal to 2, what we do is we take the second argument, right? So that is basically the value that is stored in a variable called string. Then we assign that to another variable called high, and then we are going to do, we're going to write that pattern, right? Write whatever that value is onto the register. So we'll discuss how this works later, right? So now, if the command is read hardware register, if that is the case, so what we do is we'll just read the we'll do another we do a call to another function that does this, right? That's reg read. So again, I'll describe what these $IDS hardware register, $IDS command register, all those values are. So another command is all reds, right? So if you pass this command, it basically prints out the value of all the registers, that is command, now the hardware register, the software register, right? If none of them is passed, it says unrecognized command, right? So let's look at this these constants that we described, right? So these are not available to us, these constant, basically they're the address of the registers, right? So these are not available to us directly, right? So before that we have to run a script with the ids.xml and project.xml, or we can just after making it, right, after we go into synth and then we make it after generating the bit file. So there's a C file that's generated that includes the addresses of all the registers, various registers that's there in our design. From that, we'll get these values, right? So after that, we can directly, we have written this register write and register read functions that take that address and then write to the appropriate memory location. So that's basically a DMA, right? So the bit file for the pass-through IDS was generated and that was uploaded to the data lab, to the control node basically. So this nf2 underscore top r7n dot bit, that is the bit file that was generated, and this is ids-reg.pl is the Perl script that was uploaded, right? So let's try to download this bit file and see if our design works. So yeah, as you can see, the bit file was downloaded. Now let's so before that, let's try to run the RKD. Now let's try to ping the node 0 and see if it works. So as you can see, it's working, right? Let's try ping in one. Yeah, even that works without any packet loss, I guess. Yeah, 0% packet loss. So the pass-through IDS is actually working. It doesn't do anything. It just, connects the inputs and outputs, and there's not much any functionality that so first I'll just reset all the registers. Okay, so it's the command for that. Let's see if we were successful. So yeah, uh, all the registers value has been set to 0. Now let's write a value using software, and then that value has to be byte reversed and then returned to hardware register, and then we'll read the hardware register to see if that happened. So write software register, we'll just write numerical value. Okay, so this is the hexadecimal format of that, right? So when I say read hardware register, I should see the same value but whose order is changed, right? So this is the ls byte, this is cd is another byte, 5b is another byte, right? 07 is another byte. So we have to see the order changed or reversed, right? So let's see if that's happening. So as you can see, the byte order is in fact reversed. The lower significant byte that was there, so that became the most significant byte here. Next was CD, and next is 5B, next is 07, right? So the hardware and software register interface that we have built in fact works.
Welcome to the demo for Lab 7 Part 3. First, we look at the changes which we made to the IDS.v file in order for the IDS system to work. First, when we just loaded get the bit file using the IDS.v file given, we found that it was not working. So then we went back a few steps. We compared the IDS sim.v with the IDS.v file, and we had the following observations. Here, first of all, when we go to the small FIFO, we are getting the signals in FIFO control and in FIFO data, and the same signals, the whatever the input FIFO data was getting it's in control and in data was fed to the detect 7B matcher. So that was wrong. Uh, so the detect 7B matcher and the drop FIFO should be in sync. The input data is for them and not with the input FIFO. This was the first observation which we had. The second observation being the empty signal. The empty signal was being fed a clock late. So we had to slow the in FIFO control and in FIFO data for the same. So for everything to be in sync. So these were the changes which we incorporated. Here you can see that we slowed the in FIFO control and in FIFO data for one clock cycle. We just added it in the always block. And these were the changes done to the IDS.v file. Next, swiftly moving to the demo. Here we have logged into the four nodes, the control node, the node N0, N1, N2, and N3. So here, so we reprogrammed the FPGA, and now we'll load the bit file which we generated. Uh, so we'll just do nf download. Uh, so just a second. We'll just do nf download nf top.bit. So here we are loading this bit file. So we are done loading it. We'll start RKD. RKD is somewhere here. Just sorry for the wait, guys. Just a second. Yeah. So it's startup RKD here. So we have RKD started. We are good to go. So uh, basically, we have this script to run the UDP test on all the nodes. So we'll just quickly look at the UDP test script we have created. So this is the script which we created for UDP test. This is a very simple script, which it will start the UDP servers on all the nodes. And next it will start the clients as instructed to us in the manual. We'll have to send the write messages two times and the pattern at once. So each node will send two write messages with no pattern and one message with pattern. So this is our script. So basically, this message and pattern. Now, where do we get this? These are files which we have loaded. I'll just show these files. This is message. So this is the message. We don't have have a pattern, which we'll have to set as A, B, C, D, F, G in capital, as it's not set here. We can see that this is our message, and this is our pattern. This is a pattern, and we have our pattern set here. This is the pattern file which we'll send, where we'll have to get the match, and this packet and this whole file should not be delivered to our destination. So after so first we will just use the Perl script to reset all the registers. uh, So we'll just use IDS Perl IDS reg.pl reset. Okay. And just look at all the registers. Yeah, see, so we have zero matches, zero pattern high, zero pattern low. And at this point, if we try to send any packet, all of them would be dropped. So to show this small demo, I'll just do this, ping and not, and we can see that it will take a, yeah, so all the packets are matched and it will be dropped. So we can just check that everything's working by looking at the matches. Yes, we found some matches. We see an A here. So these many packets were dropped. So almost 10 packets were dropped. So 9 to 10 packets were dropped. Okay, next we'll just clear it. We'll again reset all the registers. Reset all the registers, and we'll set a pattern. Pattern A, B, C, D, E, F, G. See, so we set a high and a low. So we have 7F, which would be our mask, A mask, which would be equal to 0, 1, 1, 1, 1, 1 appended to it. So now we can just try to run a script. Before we do that, we'll just run TCP dump on all the nodes. I think I'll take a second to do this. Give me a second. Hello guys, we are back. We are running the TCP dump on all the nodes and not N1 and N2 N3 respectively. And now we are going to just start run our UDP script. So our script will just now bombard all the packets everywhere. So yeah, see this warnings. We on total we did not deliver four. We did not get acknowledgement for four of this. So we are somewhere right with the number of messages we have dropped. So we'll just look at this. So we have just received one, two, three, and four of them. So each node sending two of this here, and each node sending two of this here, two of this here, two of this here. If we had if we had the wrong packet even delivered, we'll have to have six. So we'll look at the ASCII text files, ASCII of whatever equivalent of whatever message we got. So we'll just run this again. So here we are running the ASCII equivalent of all the message which will be dumped right now using TCP dump. Now we'll again run our UDP test.script. So here we are killing servers. We again did not receive acknowledgement for four of the datagrams here. So see, you can see all the messages here. The message one, two, three, four of them here. And this is the case with all of the nodes, one, two, three, four, one, two, three, four, and one, two, three, four. And here we can just look at the pattern which we try to send. Here, yes, see, this the one pattern with A, B, C, D, E, F, G was not delivered to any of the nodes, so it did not make it to the end destination. Yes, now we look at the packets which were matches which were found. These are the matches which we found. This is the hexadecimal equivalent of the number of matches we found, and that's about it. Thank you so much, guys. We just went through the working. We saw that all the packets which were destined to be dropped were dropped.